Welcome back. Let's continue from last time. Let's quickly finish what remains, the proof for Ehrlich-Schonowitz theorem. So last time we did the Moskine-Strauss linear algebraic symmetrization, the continuous version, and we're talking about this Ehrlich-Schonowitz theorem, which basically give a complete answer for the asymptotic problem of determining the extremal number of a general graph H, which shows that asymptotically this number is completely solely determined by the chromatic number of this forbidden graph H. When the H is non-bipartite, meaning that it has chromatic number at least 3, this completely solved the problem. For bipartite H, the problem becomes much harder. In the literature, it's called degenerate problem, and we're going to talk about that later. Okay, so for now, let's only worry about non-bipartite forbidden graph H. So how do we go about proving this? So this proof is a classical proof, a good illustration of a combination of techniques we've learned so far in the introductory part. So we start by first, the lower bound is easy. So just by taking the two-round graph and using the chromatic number, the definition of chromatic number, that works. For the upper bound, let's quickly recap what we did. We first pass from a graph G to a subgraph where we can boost its minimum degree. So we replace the average degree by minimum degree condition by losing a little bit of error term. But this is not a big issue because we start with a little bit surplus. Okay, and remember what we need to prove. To prove that H is in G is enough to prove a supergraph of H is in G, which is this complete multipartite graph with R+1 parts, which is the chromatic number of H, and each part is of sufficiently large size, say the number of vertices of H, so that we can embed H in there. So this is what we're going to prove, the complete multipartite version. And we begin by using this lemma. So we pass to a subgraph with now minimum degree at least this quantity. Okay, so the missing proof is we didn't prove this lemma of how to boost the average degree to minimum degree. And the other missing part is now we use induction on the number of parts to try to build this complete multipartite graph KTTT. The base case is trivial because when number of parts is 1, it's just an empty graph. Inductive step, we are showing that, okay, we want to build one more part, right? By inductive hypothesis, we can already build S parts. Now we want to build S+1 parts for some S at most R, okay? And last time we basically made this claim without proving it, saying that let's do double counting on number of stars like this. That's basically the idea, so that we can estimate the number of vertices, which we call Z, the set of vertices Z in the remaining vertices that has high degree to each of these parts. High means at least T, okay? If you have many these choices, then by pigeonhole, we can find at least T vertices when N is sufficiently large, so that all these T vertices, they will have some common T neighbors in each part. If they have some common T neighbors in each part, what does it mean? It means this is the new part we can add to the previous one. we obtained a complete multipartite graph with one more part. That will finish the proof. And we did this part. We did the part that if we have enough vertices with large degree to each part, then pigeonhole, we can find the desired complete multipartite graph. Okay, so to finish the proof, let's pick up from here. Let's prove how to use double counting to show that there are enough vertices of high degree. So let's go from here. Okay. So can I crop out the top? Give me a second. The sharing option. Probably, I think I don't need to show the tool bar so that we can have a larger screen, no? How do you do this? Mirror. How about this? Any difference? All right, okay. Never mind. So what we're gonna do, we want to prove that, recall, what we have now is we have a graph. Continue the proof of Berdych-Stone-Shumanovich. So we have a graph G, n vertices with minimum degree, at least 1 minus 1 over R plus 2 plus epsilon times n. Okay, and we finished the induction to embed this multipartite graph, and we just need to prove this claim that for this graph Z, and we already have this x1 dot 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 to xs, which is the complete multipartite graph, and this is the remaining set of vertices y, and we define Z. So what is Z again? Z is subset of Y, set of all vertices with at least T, which is our choice of parameter, this much neighbors in each xi, where I goes from 1 to s. Okay, so all these vertices, they have at least T neighbors, lots of neighbors. We want to show that the set of such vertices Z is large. And we have Z must be linear in N. In particular, this many. Proof. So this idea is just double counting, okay? We're gonna do double counting. We're gonna do double counting number of stars K 1, number of stars with S leaves, okay, where each center of this star, this is the center V, is down in Y, where the center V is in Y and with exactly one leaf in each xi. Okay, so we're counting such thing. You have a vertex down here. You have a star that has exactly one leaf, in each xi. The red star is the one we're gonna do double counting. First, let's give a lower bound on such number of stars. So let's let m be the number of such star, okay? On one hand, let's give a lower bound. How do we give a lower bound? So we're going to count from the perspective of leaves first. Since we require each such star must have one leaf in each set, so let's grab a S-tuple, one from each xi, and look for their common neighbors down here. Okay? If they have any common neighbors down here in Y, then any one of these common neighbor together with this S-tuple will give a star. That's how we're going to give a lower bound. So fix, this is a lower bound. Fix an S-tuple, let's call it x1 to SS in x1 times x2 times xs. Okay. Let's count their common neighbor. How to count the common neighbor? Well, let's look at the degree sum. The degree sum of xi number of common neighbors of xi in Y is at least the sum of their degree. I goes from 1 to S, right? Sum of their degree minus S, I think it's S minus 1. Wait. Let me see what's the best way to write. Okay, so how do we count it? We look at their degree sum. You sum them out as a multiset. Then the quantity that exceeds S minus 1 times N will be a lower bound on the common neighbors of x1 to xs, right? Because the worst case is that if every vertex down here has at most is not a common neighbor. If a vertex is not a common neighbor of this x1 to xs, then it has degree at most s minus 1 to this x1 to xs. That being said, all the vertices that's not good for us, that's not a common neighborhood, contribute s minus 1 times n. So the remaining degree sum will lower bound the number of common neighbors. So the number of common neighbors of x, I in y is at least the degree sum minus s minus 1 times n. So this is the common neighbors in the whole graph of this tuple of s vertices. But it could be some vertices up here. So that's minus also all the vertices up here to make sure that the common neighbors are living down here. So minus, you have S sets. Each set is of size capital T. But remember, this capital T is what? Some R, what's the number? Something like this, right? This is a number that's independent of N. So it's a constant. And S is at most. And recall, S is at most R, which is also a constant. So what really matters is this quantity. Let's count it. So this is at least, we have every vertex is of at least the minimum degree. What's our minimum degree? This quantity. 1 minus 1 over r plus epsilon n. So let's put in here. 1 minus 1 over r plus epsilon n times s minus s minus 1 times n. Okay. Minus s times t. And if you think a little bit, do the optimization, this is minimized when s is as large as possible, when s equals to r. And if you check that, this is some calculation. I leave it for you to do. Minimize when s equal to r, and you will find out that this is at least r times epsilon times n. Okay. Over 2 sec, just to be safe. So that's the just calculation, number of common neighbors. Now we have a lower bound. Let's give an upper bound on the number of such stars. Okay, how do we give an upper bound? Look at this picture again. So we're gonna count such star bounded from above by distinguishing whether this vertex is a vertex in Z or not. Okay, when it's not in Z, when it's not good, well, the worst case is that this vertex has exactly t minus 1 neighbors in one set and completely joined to everything else. Everything else is a neighbor of this vertex. So we are just barely not making into Z. Remember, the requirement of being in Z is to have at least t neighbors. So only one set is violated and just violated by 1. So you have a vertex of really large degree up there, but not making it to Z. And we're going to count making use of this set of bad vertices. And this double counting will give us a lower bound on Z. To make it precise, let's let utilizing this set Z prime, which is the set of vertices involved in at least r epsilon over 4 times the size of xi, I from 1 to s, meaning such s stars. Okay. if you involve, this is the set of vertices, that's the center of these many stars that we've been counting. Notice that a simple observation is Z prime is a subset of the set of good vertices we want to count that has large degree to hxi. Why? Because if not, then it has at most t minus 1 neighbors in one part. And this is less than r epsilon over 4 times this xi. Okay, less than one of these. And even if you are joined to everything else, the number of stars you're involved in will be strictly smaller than this number. So Z prime must be a subset of Z. Okay, so now we can double count. By definition of Z prime, every vertex, let me just write out what I just said earlier. Every vertex Z in Z prime has at least R epsilon over 4 xi, which is T neighbors in each xi. This is the proof of the observation. Yeah. Now we're gonna double count this number of stars, which is capital N, is at most from above. Well, for every vertex in Z prime, the maximum number of stars you can possibly involved in is everything. You take a vertex from each xi, 1 to s. For vertices not in Z prime, there are at most n of them. You just count all the vertices that's not in Z prime. And for each one of them, by definition of not being in Z prime, they are involved in at most R epsilon over 4 product of xi, I from 1 to s. Meaning, right? Now this is the upper bound on n. This is a lower bound oh, here, I forgot to say the lower bound. N is at least what? We count for every S tuple, we have this many common neighbor. Each common neighbor contribute to that star. So this is at least the product of xi. I goes from 1 to s. This is the total number of S tuple times each S tuple give you a, and the common neighbor of theirs give you a star, distinct star. So combining this lower bound 1 and upper bound 2, I will skip the calculation, will give you that Z prime is, and we are proving Z prime is a subset of Z, right? Z prime is at least the quantity we want, completing the proof of everything. Okay, so I will not prove that you can pass from average degree to minimum degree. That's just by removing a vertices of low degree. I will leave it for you as exercise to prove. So let's recap the whole idea. I think it's a nice classical proof. It has several nice, you can break it down into several steps, and each steps use a very useful technique that you will see that's going to be useful in many other problems. Okay, so what are the steps? The first step is a bootstrapping step. So this is a very vague term. Bootstrapping, bootstrap means you start with some condition, hypothesis, you start with some property, and somehow without using anything else, you can then derive from this property a stronger property that you can utilize. Okay, what do I mean here? We start with, you have a graph with 1 minus 1 over r plus 2 epsilon times n squared over 2 edges, right? What does this mean? This means its average degree is at least 1 minus 1 over r plus 2 epsilon times n, right? We start with the average degree condition, and we bootstrap it, we improve it to a minimum degree condition by losing maybe an epsilon here, passing to a subgraph, right? So this is what I mean, bootstrapping an average degree condition to a minimum degree condition. And then we work completely with the graph with high minimum degree. And our idea is to use induction, a nice technique on the number of parts to build this multi-part graph K, T, 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 T. After that, how are we going to build that? Remember, we're building it by induction hypothesis. You already built some parts. To add one more part, we're going to double count. We're going to say that there are many, many vertices that has many neighbors into these previous parts. And this, by averaging, then you are done, right? So this claim is many vertices, which is this set of Z, sends lots have high degree to each xi. So this proof is by double counting the number of stars that we've been doing. And the remaining step, the final step, is the one we did last time. Okay, you have this set of Z, then just by pigeonhole averaging this set Z together with this x1 to xs from induction hypothesis will give you x1, xs, xx plus 1, which is subset of Z. Okay, all these nice little tricks together. Any question? I spent a little bit more time than necessary to explain this proof because this is probably the first proof that's slightly non-trivial, not that short, and combining several ingredients. So last time I wanted to mention an application of Turan's theorem, which I forgot to. So let's do that now. So we've been saying, okay, Turan type problem is useful, not just because it's interesting on its own, it can be used to in solving some other problems that seems irrelevant to Turan type problem, to extremal graph theory. Okay, here's an application. A geometric problem. Okay, this is a theorem of Erdős. It says we have some arrangement of points in the plane. So we are in R2. You have some arrangement of points, arbitrary arrangement of points. The only requirement is the longest pair, the diameter of this, let's say these 2 points are the furthest pair of points in this arrangement. The diameter is at most 1. So 2 points cannot be more than distance 1 apart. So for any arrangement P of m points in the plane R2 with diameter one. Okay. What can we say about this? The conclusion is we can say something about the number of pairs of points that are relatively far apart. And by relatively far apart, I mean the number of pairs of points in P with distance strictly greater than 1 over square root 2. So the number of such pairs is at most n squared over 3. That's what we're going to prove. Is the statement clear? Okay, if the statement is clear, let's prove it. So I already told you this is an application of Turan. So if you think of building some auxiliary graph and apply Turan's theorem to it. And Turan's theorem saying that, okay, if you don't have a complete graph as a subgraph, we have an upper bound number of edges. That already says a lot of how we're going to approach this problem. We can upper bound the number of edges. And here we are also trying to upper bound something. So that means perhaps the edges correspond to pairs of points that are far apart. And each point is going to be a vertex. Okay, so let's try that. Proof. Let G be an n-vertex auxiliary graph with vertex sets V of G equal to P. Every point is a vertex, and X adjacent to Y in P, 2 points, if and only if the distance of X and Y is strictly bigger than square root 1 over 2. Okay? By building this auxiliary graph, our task is now, it suffices to show, this is a shorthand for suffices to show. Now suffices to show that this graph has at most n squared over 3 edges, because the number of edges corresponds exactly to the number of pairs of points in P with distance strictly greater than 1 over root 2 by definition of G. And now it looks familiar, right? So if you recall, Turan's theorem says 1 minus 1 over R times n squared over 2 E of G when it's KR plus 1 free. What's this quantity? N squared over 3. That's precisely when R equals to 3 here. So that means we just need to prove this graph G is K4 free. Okay. By Turan's theorem, we need to prove G is K4 free. You don't have 4 vertex complete graph. Okay. So let's prove that. Suppose there's a K4. Why not? Yeah. Let's suppose there exists a K4 in G. So these 4 vertices, complete graph on 4 vertices, they correspond to, in the original arrangement of P, 4 points in the plane. If you have 4 points in the plane, what I'm saying is that this K4 correspond to 4 points in the plane, okay? For any 4 points in the plane, you only have 2 types of arrangements. Either these 4 points are in convex position, or these 4 points are not in convex position. That means 1 point is in the convex hull of the other 3. So this is type 1. This is the second scenario. In either scenario, okay, in either case, there exists an angle of at least pi over 2. What do I mean by this? There exists a triangle with a angle at least pi over 2. So in this case, this is a foregone, right? If you look at this convex foregone, then sum of this degree is exactly 2 pi. By pigeonhole, one of them is at least pi over 2. And this is even simpler. You just look at these 3. These 3 sum up to 2 pi. So one of them is at least pi over 2. Okay. And why is that a contradiction? Well, now let's look at this triangle. So if this is the pi over 2, 1, and if this is the pi over 2, 1, okay, where's the contradiction? Well, you have oops, sorry. This is bigger than 1 over root, what is it, 2? This is bigger than 1 over root 2, and this is at least pi over 2. That implies this edge is strictly bigger than 1. So you find 2 points in P, xy in P, but the distance is strictly bigger than 1. That's a contradiction. Finishing the proof. Remember, our diameter is exactly 1. Any question? It's a nice, cute application. Okay. Now, so the first proof of Ehrlich-Stone-Szymanowicz is a classical one. Now I would like to give a more modern proof, which is conceptually simpler. So proof 2 of Ehrlich-Stone-Szymanowicz. This is I would say it's a modern proof using an embedding lemma. Which is from Semiradis regularity lemma. So if you don't know what it is, don't worry about it now. Let's just assume we have some embedding lemma as a black box for now. Okay, I will tell you what is this black box. So treat it as a black box. So assuming this embedding lemma, Ehrlich-Stone-Szymanowicz is very quick. There's a very quick proof. So it's conceptually simpler than the first proof. Although this conceptually simpler is building on this nice machinery, which will take a while to explain. We're going to postpone it to later. So to talk about this embedding lemma, we need to introduce a concept that generalizes the subgraph containment, which we call homomorphism. Okay, so what is a subgraph containment? Recall, subgraph containment just says you can somehow map a vertex one-to-one to somewhere else. Right? You can map one-to-one. Oops, this is not correct. Right? This is subgraph containment. Good. So what is subgraph containment? This is an injective map preserving adjacencies. Right? Injective means every vertex must be mapped to a different vertex. Preserving adjacency means if two vertices are adjacent, their image, which is here, must also be adjacent. Okay, now the homomorphism definition is very similar, but we don't require injectivity. It is just a map from the vertex set of a graph to another, preserving adjacency. that resembles more of this group homomorphism we learned in abstract algebra. Okay, we don't require injectivity. Let me write down the definition. Okay. Definition. Homomorphism. A homomorphism from a graph, let's say this is H, this is G, from a graph H to a graph G is a map, so we don't require injectivity, from, let's say, is a map phi from V of H to V of G, preserving the adjacencies, i.e., for any UV, if it's an edge of H, then its image, phi U, phi V, together must also be adjacent in the target graph G. Okay. Now let me give you an example. A very classical example, simple one, is 5 cycle to triangle. Okay. So obviously, C5 is not the subgraph of C3 or K3 triangle. Okay. But we can have a homomorphism from C5 to K3. So you don't have subgraph map, injective map, but you have a map. So let's write down this map. You can map these 2 blue vertices to, say, here, and this purple to here, like this, and red here. Okay, so you check. This is just a map from H to G. This is H. G is K3. For any 2 vertices, let's check. For any 2 vertices, let's pick these 2. These 2 vertices. So this purple vertex is mapped here. This blue vertex is mapped here. That's their image. If they are adjacent, they are also adjacent. You can check for every edge. This is true. Okay. And this picture just means all the purple ones get mapped to here. It's not injective here. Okay. So just to understand this definition, here's a remark. Using this homomorphism language, now I give a very special example. You have homomorphism to a complete graph. Okay. So homomorphism to a clique KR. Is this a homomorphism from H to, if you can find homomorphism from H to KR, that's the same as saying if and only if the chromatic number of H is and most R. These two are the same. If this is not clear to you, exercise to prove this statement. Okay? You can find the homomorphism from a graph H to KR if and only if its chromatic number is and most R. Now, perhaps I should give another example where we don't have homomorphism to complete graph, to non-complete graph. So here's another example from C7 to C5. Okay. So I will leave it as exercise for you to find a homomorphism from C7 to C5. That's the first exercise. Second, prove that there's no homomorphism from in the converse way. You cannot map C5 to C7 to find the homomorphism. There's only one way. Okay. Good. So to finish this definition, we say that if there exists a homomorphism phi from H to G, well, I should say, so sometimes when I say homomorphism, I just write H to G without writing the vertex sets, okay? It's assumed. Vertices to vertices. So if you can find homomorphism from H to G, this is also definition, we will say, we say that G is a homomorphic image of H. Okay. And here an example is K chi of H is a homomorphic image of H. If it's not clear, prove it. Now we can state the embedding lemma. I will not prove it now. We're going to prove it later using regularity lemma. So embedding lemma. It says the following. Okay. Before that, let me introduce one more piece of definition. The edge density. So let's do things in the asymptotic way. What is the edge density of a graph? G is simply you have E of G normalized by n choose 2. This is the edge density. Why we normalize by n choose 2? Because n choose 2 is total possible number of edges in the n vertex graph. So this quantity, edge density, is precisely the percentage of pairs of vertices that are adjacent in G. Okay, you can also interpret it probabilistically. Interpreting it probabilistically, what it means is that if you uniformly at random, so let's call this tau, choose 2 vertices in G, then the probability that these 2 vertices, let's say UV, form an edge in G is precisely tau, right? Because these 2 pair of vertices could be any one of these n choose 2 with equal probability, and we have this many choices to hit an edge of G. So that's the probability. These two ways to view it is useful, keep in mind. Now let's state the embedding lemma. It says that no matter how complicated a graph we begin with, then we can in terms of forbidding a graph, we can always pass to a much simpler bounded size graph where the forbidden graph becomes, we forbid all its homomorphic image. Let me state it. Let H, let me state it precisely. Let H be a graph. Then the following holds for all sufficiently large n. So what is it? For any n vertex H-free graph G with edge density tau bigger than 0, there exists, the conclusion is, there exists a graph, which actually later we call a reduced graph. But for now, not worried about this. There exists a graph R that's generated from G, somehow associated to G. There exists a graph G R with the following property. The property is, first of all, the edge density of R is almost the same as that of G. So edge density of R is at least tau minus little o1. Okay. Give me a second. If you want to be precise, I think this little o is not depending on. Give me a second. Yeah, it's depending on R. So you have some graph R, which is large but still bounded size, and this little o1 error term is small, depending on R, such that you have this first condition: you don't drop the edge density too much, and second of all, R has no homomorphic, contains no homomorphic image of H. Okay. Actually, why don't we give a, this means what? Hello? 지금 수업 있어요. 이따가 얘기해. 네. So, let's give a definition. If there is no, if a graph does not contain a homomorphic image of another graph, that just means by definition, there's no homomorphism from H to R, right? That's the definition. Let's recall. And if this is the case, we define it to be R is H home free. Okay, R does not contain a homomorphic image of H. So let me say a few words about why this is useful. Before that, let me make sure that everyone's on the same page on this little o1 term. So to be precise, I think I will do one more time of illustrating this little o1. in the future, I will not illustrate it. Okay. That means if you want to be precise, it means for any epsilon bigger than 0, and then you have for any h that's given, right? Yeah. Then there right. And this n depends, of course, bigger than n0. That depends on epsilon. I don't think it needs to depend on h. Let me see. Yeah, why not? That's right. H is a fixed graph, right? Depend on h, that's fine. Now, this r will depend on epsilon, okay? Not on this n. So that will make sense of this. If you want to be precise, here the edge density is bigger than tau minus epsilon. Okay? Good. Now, why is this useful? This is useful because, again, we bootstrap our property. What do I mean by that? Without losing much. Remember before, we bootstrap average degree to minimum degree, which is a stronger property. And we only lose a minus epsilon on the average degree from the average minimum degree from the average degree, right? We only lose something that's not harming us. Here it's the same. We go from a graph that's h-free with edge density tau. Now we go to another graph, we obtain another graph where the edge density is not dropping much. It's almost the same, okay, losing a little bit. But we obtain a much stronger property. It's not just h-free, it's h-home free. Why this is stronger? Well, trivially, there's a homomorphism from h to itself. So h-home free contains h-free as a subproperty, right? Forbidding all homomorphic image of H means you forbid a larger family of graphs as subgraph. Okay, so the remark is that we, without losing much, from G to R, without losing much on edge density, we bootstrap. So why, this is to answer why embedding lemma useful. We bootstrap H freeness in G to H home free this in R. Okay. Now, using this embedding lemma, we can finish the proof. We can do another proof of Erdős-Stone. A very conceptually simple proof. Proof 2 of Erdős-Stone-Simonovich. Lower bound will be the same. Let's just prove the upper bound. Upper bound. So what does upper bound means? Let's translate it. So upper bound means if you are H-free, right, then E of G is at most 1 minus 1 over R. And let's say chromatic number of H is R plus 1. Then the number of edges is this plus epsilon times n squared over 2. That's what we want to prove for any epsilon, right? For any epsilon, there is this sufficient large n, such that for all large n, we have this upper bound E of G. Translating it to the edge density version, this is the same as UH free, then the edge density of G is at most 1 minus 1 over R plus little o1, right? Let's just write epsilon as little o1. Okay, that's what we want to prove. So how are we going to prove that? So by embedding lemma, we can find R, apply embedding lemma on G. We find our graph R, this reduced graph, the magical graph. We know that there is some graph satisfying that the edge density. So let's call, why not call tau to be this? Okay. So the edge density of G, of R is at least tau minus little o1. We don't lose edge density that much. And furthermore, this is H home free. Okay, you don't have any homomorphic image of H. But H home free means what? It in particular implies, let's recall one of the most useful homomorphic image of H. Remember this exercise. What's the most useful homomorphic image of H? It is a clique on chi of H number of vertices. That's a homomorphic image of H. So H home free implies that R is in fact chi KR plus 1 free. Okay, remember this is definition of chi of H. Now we apply Turan's theorem on R. What do we get? Turan's theorem on R basically says the edge density of R is at most 1 minus 1 over R. Right? Turan's theorem says ER plus 1 free, E of R is at most 1 minus 1 over R, number of vertices over 2. Okay. Normalized by R choose 2, slightly bigger than R choose 2. Okay. I need to put actually a plus little o1 here. A little bit annoying, but we need to add this little o1. And this is at least tau minus little o1. Then we are done. Very simple proof. Any question? So this embedding lemma is basically reducing Ehrlich-Stone-Simonovich to Turan's theorem. Okay? So embedding lemma, all it does is reduces ESS to Turan's theorem. This is a remark. Any question? Okay, if there's no question, we're gonna move on to a new subtopic in extremal graph theory, a so-called supersaturation phenomenon. Okay. Well, let me explain what is supersaturation phenomenon. Supersaturation. So we study this Erdős-Shimonovich. What does he say? He says that okay, you have this bound here. Right. Now, by definition, now what we're going to study is we want to study the question we cared about is what if we go beyond this threshold? What if we have more edges? What happens when we have more edges than this threshold? Okay. Well, the simple answer is that by ESS, if your n-vertex graph has more than this number of edges, then we have at least one copy of H by definition, right? There would at least one copy of this forbidden graph of the forbidden graph H will appear in G. And the so-called supersaturation phenomenon is that, in fact, when we go above this bound, not just that you will see at least one copy, suddenly you go from 0 guaranteed to many, many copy. There's a jump. So in fact, we shall see that many copies emerge. Such phenomenon is called supersaturation. Let's start by a very, very simple example. But this example is not the range we're looking at. Still, it's a good example. This is a result of Erdős. No, wait. This is someone else. Who was it? Suddenly I cannot recall. But definitely Erdős generalized this result further. But let's look at the simplest case. I don't remember who. For any n-vertex graph, G, Okay? If E of G is at least n squared over 4 plus 1, maybe should I put this? Yeah. Remember, this is, what is this guy? Everyone recall, that's extremal number of K3 triangle, Mantel's theorem, right? So when we go above Mantel's bound by just plus 1, by definition of extremal number, we will see one triangle at least appearing in G. But this theorem is saying not just you will see one triangle, there's actually at least n over 2 floor meaning triangles. G contains at least this many triangles. And this bound is tight. You cannot ask for more. Okay? Construction is very simple. You have n over 2 floor, n over 2 ceiling. You add one edge here. So this graph has exactly this many edges. And the triangle all utilizing this edge, that's precisely size of this part, which is here. Okay? This is a supersaturation. Whoa. In the framework of supersaturation. But today, we're going to look at things asymptotically. So asymptotically means we are always living in the dense world. We normalize things by quadratic in n term, n choose 2, right? You look at the edge density. So here, the edge density of the graph still 1/2. Normalized by n choose 2, this is roughly 1/2, okay? It's not very much different from without this 1 or not. So we care more about what happened when you have edge density strictly bigger than 1/2. Let's look at things asymptotically. But we consider asymptotically asymptotic version. Okay, what it means is look at graphs with edge density above ESS. Okay, so to write things in asymptotic way, we've already defined edge density. Let's also define Turan density to make things cleaner, because otherwise we will always have this little O1 term, which is a little bit annoying. So to do things in an asymptotic way, let's define Turan density that will help us get rid of this, and it's equivalent to this statement, all right? So how do I do that? Definition. Given the graph H, its Turan density is, we'll write pi of H to be, you look at the extremal number of H, and as usual, this is about the number of edges in the n-vertex graph, that's H3. If you talk about number of edges, then the right normalization factor is n choose 2, the maximum possible number of edges. But to get rid of a little O1 and look at asymptotic behavior, we're going to take limits when n goes to infinity. Okay. Well, if you see this definition, the first question is it well defined? And we will see soon that the answer is yes. It is well defined, meaning this limit exists. We're going to prove it in a little bit, but before proving it, let's first rewrite Ehrlich-Stone-Shumanovich in terms of this asymptotic version. So Erdős-Thom-Schoonovic basically in this language is saying that for every graph H, its two-round density, okay, is equals to 1 minus 1 over chi of H minus 1, right? The little o1 disappear. It becomes much cleaner. In other words, one can also view this two-round density is basically the maximal edge density of a graph G. That's H free, n vertices, right? The maximum edge density of an n vertex H free graph G. Well, okay, not quite the limit of it, because we take the limit, more or less something like this. Okay, so let's first prove that this limit is well defined. It exists. Actually, some of you, if you're in the winter school on this hypergraph two-round problem, this is proved already. So let's do that again here. So I want to do this proof because you use another useful technique is by, in a sense like a pigeonhole or averaging. It's a clever averaging by random sampling, okay? So we're gonna prove this theorem. That this two-round density, the limit is well defined for any graph H. For any graph H, its two-round density exists. The idea is by averaging. Well, random averaging and sampling are the same thing, okay? Proof. So what we're gonna do, here's the idea. We want to prove this guy exists, right? Let's copy it here. We want to prove this limit exists. Okay, let's actually define, look at, this is a sequence of number parameterized by n. Let's define it. Let alpha n to be this extremal number normalized by n choose 2, which is obviously at most 1. Edge density is obviously at most 1. And it's also at least 0. Some number between 0 and 1. Suffices to show that this bounded sequence an is monotone. I mean, it's actually in particular non-increasing. Okay. Non-increasing, so it keeps dropping. It's decreasing. Okay. If this is true, then by monotone convergence theorem, we know that the limits of alpha n in this language, pi of h is limits of alpha n, right? If this is true, then monotone convergence theorem says pi of h exists. So how do we prove this? By averaging. basically we say that, here's the idea. This is your graph G. We're gonna average over all n-1. This graph has n vertices. We're gonna average over all n-1 vertex subgraph. Look at the edge density there. Okay, and we can show that that would implies alpha n is at most alpha n-1. And that will be enough. If this is true for every n, that means it's a non-increasing sequence, right? And this averaging on n-1 vertex subgraph is done in a probabilistic way. So that's why I write this random sampling. Okay, so our goal is show that alpha n is at most alpha n-1. If we can prove this, we are done. So how to prove this? As I said, you take an n vertex H3 graph G, that's extremal. Extremal means E of G equals to EXN H, right? So we have alpha n equals to, E of G over n choose 2. No problem. Now how do we sample n-1 vertex subgraph? Very simple. We just uniformly choose a vertex V and excluded the remaining will be our graph, random graph. Let's call it G prime. Uniform random choose a vertex, throw it away. The remaining is an n-1 vertex graph. Let's do that. Uniformly at random, that means every vertex is chosen with probability 1 over n, same probability. Delete a vertex V, so this is V, from G. Delete vertex V from G. Oh, it's almost from, we have 5 minutes. So let's finish this proof. This proof is not so long. Delete the vertex V from G. We will get a graph G prime. That's the subgraph G prime. G minus V. Okay. Now let's compute. G prime is a random graph. This is random, right? Because V is a random vertex. So induce a random n-1 vertex graph, random n-1 vertex subgraph of G. So its number of edges is also a random variable. Let's compute its expectation. So to compute that expectation, let's look at one edge. Fix an edge, E in G. What is the probability that E lies in G prime? Okay. E is in G prime if and only if this random vertex is not in E. If and only if your edge does not look like this, right? So what's that probability? The probability is what? You fix this E, you have 2 endpoints, and V is uniformly chosen with probability 1 over n over all vertices. So this vertex is possibly V with probability 1 over n. This is also 1 over n. So that's probability exactly 2 over n that V is in E. Okay. Oh, I write it wrong. This is actually V in E. Probability is 2 over n. So that implies the probability that this edge is an edge of G prime is 1 minus 2 over n. Okay? Now, linearity of expectation implies the expecting number of edges in G prime equals to sum of all edges in G, probability that E is in G prime, right? And every one of them has the same probability. This equals to E of G times 1 minus 2 over n. Okay, but what is E of G? E of G is, by definition, alpha n times n choose 2. One minus 2 over n. Some calculation shows that these two, if you multiply together, is exactly n minus 1 choose 2. I will not do the computation. Okay, so we get this. What does it mean? Remember, first moment method says what? If you have a random variable whose expectation is something, then there must exist the outcome of this random variable. There must exist the outcome of G prime. There must exist the choice of V so that the induced G prime, the number of edges is at least this much or at most this much. Either case is possible. And we're going to do at least. So this implies there exists a choice of V such that E of G prime is at least the expectation of E of G prime, which equals to, why it keeps happening, which equals to alpha n times n minus 1 choose 2. We are almost done. Remember, G prime is a subgraph of G. So that implies, because G is H-free, so G prime is still H-free. Okay, what does it mean? That implies that the number of edges of G prime is at most, by definition, is an n minus 1 vertex graph, is at most the extremal number of H on n minus 1 vertices. And what's this? This, by definition, is alpha n minus 1 times n minus 1 choose 2. That's our definition of alpha sequence. Okay? Look at this. So maybe I use 1 and 2, right? So 1 and 2 implies alpha n is at most alpha n minus 1. And we are happy. Question. Any question? No? If not, then we're going to continue next Tuesday